Algebra 2, Chapter 16.3, Exercise 1 through 14. In this section, we're going to go about solving logarithmic equations. I'm going to do the odd number problems in this set. Now, problems 1 through 6 involve solving equations graphically. So the strategy here is to take each side of this equation and enter each side in your calculator as a function. So the left side we enter as y equals 8 plus log x. And the right side of the equation we enter as y2 equals 2 log x minus 12. Now, in case you don't remember, when you see log x, what does that really mean? Well, that means that this, by default, has a base of 10. So that's what we have to look at. So now let's go to our graphing calculator and enter each side. And previous to starting this video lesson, I entered these two logarithmic functions. And when I press a standard window view, this is what we get. And we see only the first function here, the 8 plus log x, and not the red one. And to see where the red one starts, we can fiddle around with the window. I'm going to put down what a good domain would be. Our x max is going to be 2 times 10 to the power of 20. So that is, I don't know how many quadrillion. Our x scale I'm going to put down as 10 to the power of 19. And our y minimum I'm going to put at 0. Our y maximum I'm going to put at 35. So let's see what we have here. We'll see if we have an intersection point between the two graphs. And it looks like we do somewhere in the middle. So to find what that value is, we press second, trace, 5, enter, enter, enter. And so we get x equals 1e20. Let's examine what that means. So x is equal to 1e20. Okay, what that means is x is equal to 1 times 10 to the 20th power, or x equals 10 to the power of 20. So that will be our answer for problem number 1. Again, it's the x value of the intersection point that gives us our answer, not 28, but 1 times 10 to the 20th power. Now let's go to problem 3. We have the equation 10 equals 3 log base 2 of x. So as we did in problem 1, if we enter the left side as y1 equals 10, and the right side of the equation is y2 equals 3 log base 2 of x. Now what we're going to use is something called the change of base formula. I'm going to review what that is. And the reason I'm doing that is because on our calculator, we don't have a standard log base 2 key. We just have a log key or a natural logarithm key. So the change of base formula is if we have log base a of b, that is going to be equal to log of b over log of a. And consequently, we can rewrite this y2 as 3 times log of x over log of 2. And so now we can go to our calculator and enter each of these functions. So we have y1 equals 10 and y2 equals 3 times log of x over log of 2. And then if we go to a standard window, we press zoom 6. We see almost an intersection point. I'm going to go ahead and change the window a little bit. One thing you notice on the graph is that in a true logarithmic function, we're not going to have our domain that's going to be greater than 0. So usually we're going to be working on the right side of the y-axis. So x minimum I'm going to put as 0, x maximum at 15. We're going to put y minimum at negative 10. I guess put it 0, and then y maximum at 15. I think we should see an intersection point here. And yes, we have it. So we're going to press the sequence here, second, trace, 5, enter, enter, enter. So we get x is equal to 10.079368. So we're going to say x is approximately equal to 10.079. So that will be it. Our answer for problem 3. Next, problem 5. We have the equation 0.2 ln x, and ln x is equal to the log base e of x. So let's write our two equations. We have y1 equals 0.2 ln x plus 5, and we have y2 is equal to ln x minus 6. So let's go to our calculator again. There we go. So we have 0.2 ln x plus 5 ln x plus 5. And for y2 we have ln x minus 6. We go to a standard window again, zoom 6, and this is what we see. We see these two curves, but they are not anywhere close to intersecting. So let's go ahead and change the window. For the window, I'm going to put x max value of 1 million. And I'll put our x scale as 100,000. And then y minimum, y max, I'm not sure exactly where these are located. I'm going to go from negative 20 to 20, hoping that we get our intersection value there. Graph. Yeah, we're going to see our intersection point right there. So we could have got it tighter on the y value, but let's go ahead and find the intersection point second. Trace, 5, enter, enter, enter. So we get 936,589.16. So x is equal to 936,589.16. Okay. Now, the next section of exercises here, starting with 7, has to do with solving these equations. And it doesn't really give a method here, but what they mean here is solving algebraically. So let's go ahead and solve these algebraically. And also we're introduced to the word extraneous solution. And we looked at properties of logarithms earlier. I think we came across that solving rational equations. We looked at extraneous solution. Extraneous solution is not a real solution, but it's a solution created during the process of solving usually a logarithmic equation or a rational equation. So right now for number 7, we have log base 9 of 4x plus 5 is equal to 2. Now we're going to use a property of logarithms here, and that is this one. If we have log of something, log base 9 of a, we'll say, we can go ahead and rewrite this by as 9 to the power of log base 9 of a. And what happens is 9 to the power of log base 9 will cancel each other out, and we're left with a. So we're going to use this principle, and we're going to, on the left side, rewrite this as 9 to the power of log base 9 of 4x. Let me rewrite that a little more legibly, I hope. Log base 9 of 4x plus 5 equals 9 to the power of 2. So we've taken 9 to the power of the left side, 9 to the power of the right side. And on the left side, 9 and log base 9 cancel each other out. So on the left side, we have remaining 4x plus 5 is equal to 81. And then we can go about continuing to solve by subtracting 5 from both sides of the equation. We get 4x is equal to 76. Now we can divide both sides of this equation by 4. So we get x is equal to 19. And we can check our answer by substituting back in 19 in the original equation for x. So here will be our check. Now in this set, I'm not going to check every problem solely in the interest of time. So this could be log base 9 of 4 times 19 plus 5 is equal to 2. And so 4 times 19 plus 5 is going to be 76 plus 5, or 81. So what we have on the left side is log base 9 of 81. On the right side, we bring down 2. So now we can ask ourselves the question, what power do we have to raise 9 to get 81? Well, 9 squared is 81, so the left side of the equation is 2. So 2 equals 2, so that's a check. So x equals 19 is our correct solution to problem 7. Next, let's go to problem 9. We have log base 2 of x plus log base 2 of quantity x minus 4 equals 5. So what we're going to use here is called the product property of logarithms. And I'm going to summarize what that is. If we have log base, we'll call it log base 2 of a plus log base 2 of b, we combine these two separate logarithms, since they have the same base, as log base 2 of the product of a and b. So let's apply this principle here on the left side. So on the left side, what we get is log base 2 of x times quantity x minus 4. And the right side, we bring down the 5. And now distributing, we have log base 2 of x squared minus 4x. And on the right side, we have 5. Now, we're going to use the same principle we did in problem 7, is we're going to take 2 to the power of log base 2 of x squared minus 4x equals 2 to the power of 5. So we took 2 to the power of each side. On the left side, 2 to the power of log base 2 will cancel each other. So what we're left with on the left side is x squared minus 4x. On the right side, we have 2 to the 5th power, which is 32. And now we're going to continue to solve this quadratic equation. Let me go ahead and rewrite this x squared on the left side, not super legible. Yeah, it looks a little better. So subtracting 32 from both sides of the equation, we're left with x squared minus 4x minus 32 is equal to 0. Now we're going to try to see if we can solve this quadratic equation by factoring. So usually when we factor a quadratic trinomial, we will have two linear factors. And so we look at x squared. What are the factors of x squared, x and x? Now we're going to look for two numbers which, when added together, equal -4, but when multiplied together equal -32. Well, 32, we can try 8 and 4. Okay, it looks like those numbers are 4 apart, and so these are the two numbers except the signs. We have to make the signs right. So we have -32, so one of these numbers, 8 or 4, is going to be negative, the other positive, of course. We have minus 4x, and so the negative number is larger, so we're going to have x minus 8 times quantity x plus 4 is equal to 0. And now we can use the zero factor property of algebra and set each of these factors equal to 0. So we have x minus 8 equals 0 and x plus 4 is equal to 0. Now we can solve each of these equations for x. And we have x is equal to 8. And then on the other equation, we have x is equal to -4. Now we can try to substitute back into the original equation. And if we substitute -4 back into the original equation, log base 2 of -4. So what power do we raise 2 to equal -4? There's no such number. So x equals -4 is what we call an extraneous solution. Now, I'll just box this in as an extraneous solution. Now, it's possible to have no real solutions also, so we're going to go ahead and examine 8. If we plug 8 back into the original equation, log base 2 of 8. So what power? So if we have log base 2 of 8, what power do we raise 2 to equal 8? Well, that's going to be 3. And for the other part of the other term, we have log base 2, and we have 8 minus 4, which is 4. So what power do we raise 2 to equal 4? Well, that's going to be 2. So of course we get 5 here, so that checks out. So x equals 8 is what we call a real solution. Next, problem 11. Here we have 2.4 log base 4 of x equals log base 4 of 3x. And again for this one, on the right side, I'm going to rewrite the left side, 2.4. 2.4 log base 4 of x. And on the right side, we're going to rewrite this log base 4 of 3x using the product property. So we're going to write this as two separate logarithms. We're going to write this as log base 4 of 3 plus log base 4 of x. We put plus 1 right here. And so now we have two like terms on both sides of the equation, and that would be log base 4 of x. So we can subtract log base 4 of x from both sides of the equation. And we have that canceled on the right side. So we have on the left side now 1.4, 2.4 minus 1 is 1.4. We have 1.4 log base 4 of x is equal to, on the right side, log base 4 of 3 plus 1. Now we're going to continue to solve by dividing both sides by 1.4. And the next thing we're going to do is rewrite this using the change of base formula. So log base 4 of x is equal to log x over log of 4. And on the right side we have, I'm going to rewrite this log base 4 of 3 as log 3 over log 4 plus 1 over 1.4. And now we're going to multiply both sides of this equation by log 4. So we multiply both sides by log 4. And the right side we have times log 4. We have left over log x is equal to log of 4 times log of 3 over log of 4 plus 1. And it's going to be all over 1.4. Okay, so now what we're going to do is, I'm going to come right up here, we're going to take 10 to the power of each side. So we have on the left side 10 to the power of log of x is equal to 10 to the power of log 4 times log 3 over log 4 plus 1 over 1.4. And this is an exponent of 10. So we have 10 to the power of log, base log of x is x. So x is going to equal all this on the right, which is 10 to the power of log 4 of log 3 over log 4 plus 1 over 1.4. Now this is quite a handful to enter in the calculator, so what I did previously is I entered this in the calculator and I had to be careful, very careful entering, but I did. So we ended up with x is approximately equal to, looks like 590,58999. I'll say 5.8999. And we could enter this back into the equation and see if we got it right. It would take a little bit of a process. In the interest of time, I'm not going to do that here. But let's go on to this last one that I'm going to work out anyways. Problem 13. We have log base 5 of quantity 4x plus 6 equals log base 5 of quantity 8x minus 2. And so basically what we have is, since it's log base 5 of each of these, we can rewrite this as 5 to the power of log base 5 of 4x plus 6 equals 5 to the power of log base 5 of 8x minus 2. And so 5 to the power of log base 5 cancel each other on each side. And you should be able to see that just because you have everything else the same with the log base 5, we would know that 4x plus 6 is equal to 8x minus 2. Now we can just solve for x. What I'm going to do first is, I guess, I'm going to keep the unknown on the left side, so I'm going to subtract 8x from both sides. So the left side now, we have negative 4x plus 6. And on the right side, we have negative 2. Next, if we subtract 6 from both sides, we have negative 4x equals negative 8. And now if we divide by negative 4, we have x is equal to 2. And to work this out, if we have, I'm going to just do a quick check. If we write this as log base 5, so this will be our check. We have log base 5 of 4 times 2 plus 6. So 4, so 8 plus 6 equals, on the right side, log base 5 of 16 minus 2. So we end up with log base 5 of 14 equals log base 5 of 14. Check. So and we verified our answer is x equals 2. And number 14 is right here. You can look at solving this. So again, we've used some of the properties we examined earlier in section 16.1. I hope this has been helpful. Good luck, and thanks for viewing.